Welcome back, everyone, and we just wrapped up the integral test, and now we want to take a step back and see if we can, estimate the sum in some reasonable way. We can always find the partial sum, right, because that's just a sum of some finite number of terms, but between if we sum the first n terms, right, we have terms n plus 1 off to infinity that we still need to add up, and we want to see if it is convergent, like how big is that remainder? Because knowing how big that is means that, maybe we need to add more terms to be within a certain range of accuracy. But anyway, let's just kind of look at this. So we have a sequence an, and we suppose it's convergent, and we have a limit. Or the limit of the partial sums is s, and that is finite. Then we can say, okay, here is the remainder. So we know the sum of the first n terms, right? Sum of the remaining terms. And this same thing, we can say, well, that's going to be the entire sum of the sequence minus Sn, minus the first n terms, which, big surprise, okay? But now, if we know this series was shown to be convergent using the integral test, we can actually say a little bit more. We can say that, and we know the function is decreasing, so then we can say that this remainder is going to be less than the associated integral from n to infinity, because that's going to be, so we're only adding the function, or the function values corresponding to every natural number, so on and so forth. So this is going to include everything, both natural number and non-natural number, in its sum for the integral. Okay, and if we look at this just a little bit further, then we can also say that for the n terms, and then if we look for n plus 1, that is going to actually be bigger than Rn, so we have kind of this double-sided bound. Okay, so it would be here, and so let's just kind of see this in a diagram. If we look at this in a diagram, okay, here, let's say we have our function, and we know it's positive, decreasing, continuous, so this is going to be our function f of x. Okay, and then we have the values, here's n plus 1, n plus 2, and then n plus 3, so on and so forth. Okay, and then the associated values of the function the associated sequence values are here, so this would be, an plus 1, and then here and here. Okay, now if we wanted to estimate the remainder for, so let me do this in black, we want to use this line to estimate the integral from n to infinity of f of x dx. Okay, we're just going to estimate. We won't show it, but we're going to estimate. So that would be, we first learned about estimation of sums by using Riemann sums. So we'd have something like this, and then something like this, and then like this. If we'd have to use left-hand sum, so that's an overestimate, right? And if we were to do an estimate for n plus 1 to infinity, right, that would be, we could estimate that using, and we still have to estimate this region here between n and n plus 1, so that would be, we'd have to use right-hand points, a right-hand sum, so we'd have this, and this would end up being an underestimate. So that's kind of the idea behind where this estimate for the remainder comes. We know it exists somewhere between these two integrals. Okay, so to summarize all this, we have to have a function, okay, satisfying all the conditions of the integral test, positive, continuous, decreasing, and we have to know that it's convergent by the integral test, okay? And so then we can estimate the remainder by saying it's sandwiched between these two estimates, which we said previously, okay? And if we were just to rearrange this and add the first n terms to each side, then we really get an estimate for the sum. So that's all we did. We added Sn, and this is really Sn plus Rn for S, and then we added Sn there as well. Okay, so we can estimate the sum of the series too if we know the remainder. Okay, so now how or why is this useful? Let's see an example. Okay, so we have this and we want to find the partial sum, okay, and then estimate the error in using this as a sum of a series, and then we have a whole bunch of other things to do. Okay, so for part A, S10, I'm going to tell you you can do the calculation if you would like. I got 1.08203. Okay, so then what we can say is that if we're looking at R10, okay, so the remainder after the first 10 terms, that's going to be somewhere between, on the upper side, it's going to be, the remainder is going to be less than from 10 to infinity of 1 over x to the 4 dx, and on the lower end it's going to be bigger than from 11 to infinity of 1 over 4 x to the 4 dx. Okay, and cranking this down, you end up getting 11 to the minus 3 over 3 is less than or equal to R10, and less than or equal to 10 to the minus 3 over 3. Okay? So that gives us the error estimate in approximating the sum. We're saying the remainder is between these. Okay? For part B, it says use the sum estimate with n is equal to 10 to give an improved estimate. So improved estimate of the sum. So if we wanted to find the entire infinite sum, right? So if I'm saying that this is equal to S, then I can say for part B that S is going to be less than or equal to my estimate that I found before, so S sub 10 plus this 10 to the minus 3 over 3 on the upper side, and on the lower side it'll be this S10 plus 11 to the minus 3 over 3. Okay, and so this gives me a decent range, and really the difference isn't too significant. On the lower end, I got 1.08228 as an estimate. Oops, and I wrote that wrong. This should be over 3. Less than or equal to S, less than or equal to, and here I got 1.08236. So we're within, what, 3 10,000ths of each other? Or 1 10,000th of each other. Okay. For part B, we want to find the value of the sum of n, so the partial sum is within that. Now this one is actually the more interesting question. For part C, what you want to do is you want to say that the partial sum, so the difference between the sum and the partial sum, we want to find the value of n is less than 10 to the minus 5th. Okay, so then S minus Sn, that's the remainder, right? Less than 10 to the minus 5. Okay, and then we know that this means that on the upper end, we want to find the term n from n to infinity, so that 1 over x to the 4 dx is less than or equal to 10 to the minus 5. Okay, so then we can evaluate this, and long story short, we end up getting, you have to do a little bit of work, but you end up getting 1 over 3n to the third is less than or equal to 1 over 10 to the 5th, and then solving this, again, you have to do a little bit of work, but n is going to be greater than or equal to 32.18, so n has to be 33, so then for it to satisfy this condition, because otherwise 32 it won't work. Okay, so the setup here is more important. This stuff gets very computationally intense, so just kind of stick with it and have a calculator handy.